Every time you load a modern web application, your request is likely hitting a database scattered across thousands of servers, spanning multiple continents. But try asking a traditional single-node Postgres database to execute a standard nested loop join across those geographical distances, and the system breaks down. The network latency alone will stall the operation. For years, data engineering forced a choice. You could use NoSQL systems to achieve horizontal scale and high availability, abandoning strict schemas. Or you could keep your relational logic and ACD transactions, but remain trapped on a single machine. Executing a standard SQL query across shards separated by thousands of miles means waiting for light to travel back and forth through fiber optic cables for every row correlation. The math simply does not scale. Consequently, engineers spent decades compromising. They either built complex application-side logic to handle NoSQL's lack of relations, or they accepted the hard limits of a monolithic database. Google's Spanner solves this by layering a strict SQL engine directly on top of a distributed consensus core. It wasn't originally designed this way. Spanner began as a highly available key-value store and evolved over 7 years into a fully featured relational database. To understand how it works, we need to track a specific query. We are going to submit a top K aggregation with a join and a where clause, filtering for a specific nested array of customers. Executing this text globally requires stripping down and rebuilding how a database handles query compilation, data routing, and failure recovery. To survive the latency of the open internet, Spanner has to dissect the query and mathematically bound the required data long before a single physical disk is read. This diagram maps Spanner's physical topology. The universe is divided into administrative zones. Within each zone, a zone master assigns data, while location proxies route client requests. The actual work happens at the span server. This is the core worker node serving data directly to the client. Looking at the span server stack, the underlying storage layer is Colossus. Above it, the tablet layer maintains key-value mappings, stamped with commit times. Next sits the Paxos state machine, guaranteeing synchronous replication. At the top, the participant leader coordinates two-phase commits. Here is the routing problem. The SQL text we submitted has no idea which of these isolated, globally scattered Paxos tablets holds the specific customer rows it needs. A raw key-value Paxos architecture cannot read relational data. To bridge this gap, Spanner relies on a highly specialized query compiler. The moment our SQL query enters the system, the compiler strips away the text syntax and transforms it into a relational algebra tree. This flowchart illustrates the distributed execution plan. The central distributed union operator ships subqueries to individual shards. Dotted lines indicate partitionability, pulling the union up the tree to push computation down. Now, the top 5 limit and group by aggregation execute locally on each shard. Computing aggregations directly beside the physical disk prevents millions of raw rows from entering the network. By compiling for distribution first, the query shrinks the data payload before network transit begins. Even with computation pushed to the edge, searching a petabyte-scale table shard row by row will time out. To prevent this, Spanner uses compile time rewriting. This diagram shows a filtered scan expression normalized into a tree of correlated self-joins. Inside scan 1 and scan 2, the massive filter expression is mathematically pruned. Each scan receives only the specific variable references it needs. At runtime, Spanner uses this filter tree to calculate exact key ranges via interval arithmetic. Bottom nodes intersect conditions at AND operators, resolving variables into point ranges. At the top OR node, they combine into a mathematically bounded interval, narrowing the search perfectly. The system extracts 2 types of boundaries. Distribution ranges tell the network which specific shards to route the query toward. Seek ranges tell the physical disk exactly which sectors to read. By mathematically targeting only the strictly necessary disk sectors, interval arithmetic prevents the query stalling under a massive linear scan across millions of remote rows. But our query still contains a join. In a naive distributed system, correlating keys across independent shards would trigger a network remote procedure call for every single row. Spanner mitigates this using the distributed apply operator. It handles joins across sharded tables by moving data in batches. The operator evaluates filters for entire row sets simultaneously, merges them with shard boundaries, and sends dense batches across the network in parallel. This batching technique fully decouples the total row count from the number of network round trips, cutting massive amounts of compute time out of the equation. But hardware is volatile. A physical server might lose power, or the placement driver might migrate a shard mid-execution. Rather than failing the query or writing massive intermediate results to persistent storage, Spanner relies on a streaming execution model powered by restart tokens. These opaque tokens accompany every batch of results. They continuously track the precise execution state and the primary key progression of the query. But these restarts are only valid if the data remains perfectly consistent throughout the query's life. If a query resumes on a different replica, it must see the exact same database version, a challenge requiring a globally synchronized clock. This is where the TrueTime API comes in. Using GPS and atomic clocks, TrueTime allows every span server to quantify its exact clock uncertainty. If the uncertainty is too high, the system waits it out before committing, ensuring every transaction is assigned a globally irrefutable timestamp. This enables strict snapshot consistency across the entire network. We've traced the logic through the network, but the final bottleneck lies directly on the physical disk. Spanner originally inherited Bigtable's SS table, a row major structure optimized for NoSQL workloads. Forcing highly optimized SQL queries into row major trees meant reading vast amounts of irrelevant data to evaluate a single field, creating severe I/O bottlenecks. To fix this, Spanner implemented RESI, a blockwise columnar format. RESI physically segregates active multi-version data from older inactive data. This layout perfectly maps to the exact seek ranges generated by the filter tree, ensuring the disk only spins for the data the query actually needs. Our query has now completed its lifecycle. Compiled into a relational algebra tree, mathematically bounded by filter trees, batched across the network, routed by Paxos, and pulled directly from columnar storage. This exact pipeline ensures that relational data can traverse the globe without triggering massive overhead or breaking during a hardware failure. It proves that global scale does not require abandoning rigorous schema. Developers no longer have to choose between NoSQL's high availability and the strict ACID compliance of a relational database. Spanner demonstrates that with enough engineering rigor at the compiler and consensus layers, strict relational mathematics can govern data at a massive scale.